that was just a test. So I think we're still waiting for the speaker. I like the way it did that screeching sound initially because it sounds like a high school, whatever, gym, high school gym. Oh, here we have our speaker. So are you ready to go? Because then I'll introduce you. Okay. Everybody should, feel free to come forward if you want. I think there's space. But thanks so much for everybody to attending the talk today. It's my great pleasure to introduce Joseph Howard from NASA Goddard Space Flight Center. And for those who aren't familiar, Robert Goddard invented the rocket, okay? And so the Goddard Space Flight Center is named after him, and it's located in the Washington, D.C. area, but also there's Wallops Island where they actually launch rockets. Isn't that true? It was actually, maybe that's, nowadays they launch the really big rockets from Florida and Texas. But anyway, so Joe, we met Joe because we were lucky enough to get him to give a talk at a conference. It was supposed to be a keynote talk, and it was just everybody's socks were knocked off, and we're like, we got to get Joe out here to give a talk at Purdue. And Joe has a very interesting background. He was in the Navy, where he was a submariner, which I have infinite respect for submariners because I'd be afraid to be in one of those submarines under the water. And then the other thing is that he got a PhD at Rochester Institute of Tech. University of Rochester. I can't believe I just said that. Okay. University of Rochester in the Institute of Optics, which is really famous for the area of phase retrieval because the guy who invented phase retrieval, Jim Feenup, is there. And also, so then since then, he's getting his PhD. He's been working at NASA in, is it the phase retrieval group, actually?
The optical telescope alignment and design. I'm a designer.
Okay, optical. So he can give you the details. Optical telescope design group, and he's going to talk about the Hubble. I mean, it's not the Hubble. the Webb telescope and the telescopes that are going to follow it in the future. So with no further ado, Joe, thank you so much. And I think you have a wireless mic, so you don't need.
I do. All right, can everybody hear me? Yes. Excellent. We're good in the back for everything? Okay, well, thank you very much. Again, I'm Joe Howard. I'm a NASA engineer, and it's good to be here in the land of engineers. But first of all, thank you. I always say thank you when you, my audience here hopefully are students. So whenever you give a chat, always try to say thank you. So thank you to Stanley and Charles for the invitation to speak, and all of you for coming to listen. It's really fun doing outreach for NASA. Because we do fun things, so it's good to talk about them. I got here early yesterday. I was able to take a boiler up. Is that the phrase, right? So it's really good to be back home again. And if you don't know what that phrase is, you haven't been in Indiana long enough. But I married into a family that has 50 years straight going to the Indianapolis 500. So that's one of the photographs from years ago. And that 50 years was broken with COVID, like many other things. But I'm a band geek at heart. When I went to undergrad at the Naval Academy, I was a drum and bugle corps commander, so I'm a big fan of the band, and Purdue is always there at the Indy 500. In fact, if any of you have contacts for who owns that really big drum, I would love to go visit it and take a whack at it while I'm here. And I'm here the rest of the day, so come see me afterwards if that's the case. Boilermaker is in my blood. My grandfather actually came here, and he was a mechanical engineer, and this is a picture of him with all of his frats frat buddies, and I actually walked by the old house on campus, so that was kind of cool to get a taste of the past. All right, so here's what I'm going to talk about. Why we build space telescopes, just to set the motivation. Optical design of space telescopes, because that's what I do. I'm an optical designer. Fundamentally, I'm an optical engineer, but design is my specialty. And then I'm going to talk about NASA's decadal survey telescopes. And these telescopes are the ones we build typically every 10 years, and they're for major purposes. We call them flagship observatories. So I'll quickly go over Hubble, Chandra, Spitzer, and Sophia, but I will spend the bulk of my time on James Webb, because that's what I personally spent 2 decades on, from the beginning to the recent commissioning of it. Roman is coming up next. I'll briefly talk about that, and then I'll introduce the Habitable Worlds Observatory, which is the next big one that's coming up for the 2030s. Okay, so NASA space telescopes. So some questions to begin with. Why telescopes in space, right? Why space and why NASA? And I did manage to find a very famous NASA person on campus, and I got a quick selfie with him. Okay, so why telescopes? Well, telescopes are the natural instrument to image things far away. You typically need to collect as many photons as you can, and that means a large primary mirror or something like that, and then to focus it down onto some sort of detector. So typically, to do imaging, telescope is what you want to do. You can also use telescopes to indirectly image things. And one of the missions I won't talk about, but it's relevant, is the laser interferometer for space. So if you've heard recently about detecting gravitational waves on the ground, LIGO is the name of the instrument, we're actually studying a concept to do it in space. And in that instrument, you have telescopes far away pointed at each other, and you measure the amount of space change between it as a function of time. And then that helps you determine if a gravity wave has just gone by. Okay, so why space? Well, the 2 main reasons why we put telescopes in space is, number 1, no atmosphere. Without atmosphere, you don't have to worry about turbulence. You don't have to worry about absorption from the atmosphere, so you can see a whole variety of wavelengths. Space is very stable. So you don't have the Earth vibrating, wind vibrating your instruments, all that sort of stuff. And you can orbit with a constant sun exposure if you put yourself in the right location, such that temperature isn't changing across your very delicate instrument. So, and when temperature changes, you know, material properties change sizes and things can change. So you don't have to worry about that if you can control that. And finally, for infrared systems, you can get very, very cold, which is good for observing in the infrared. So why space? Here's a graph of atmospheric absorption. Essentially, on the x-axis is the wavelength, you know, going from 0.1 nanometers to really big. And this is the opacity, so things that you cannot see. So if it's 100% opaque, you can't see that on the ground, so that's a reason to put something in space. Here's our visible spectrum with the rainbow right here. We have many telescopes on the ground, but we also have some in space. But there's a really good reason to put infrared telescopes in space, because a lot of that you really can't see. Radio waves, on the other hand, you have complete visibility from the Earth, but you also have a lot of noise from the Earth. So there's even talk about putting radio telescopes on the moon behind, so on the far side of the moon. All right, very stable environment. In order to get a really good spot that's far away from the Earth, one of the favorite places to put telescopes nowadays is at what we call Lagrange points. And these Lagrange points are stable places in the Earth, Sun, gravity system. And just think of that as a point where you can actually place a marble, and that marble in space would neither come towards the Earth or away from the Earth or towards the Sun. But L2, which is behind the Earth and it orbits with the Earth, is a gravity-neutral point between the Sun and the Earth, and that is a new favorite place to look away from the Earth, because the Earth is behind you, and you don't have to worry about that. If you're building a telescope to look at the Sun, though, L1 is a great spot. The background of space is very cold. So if your instrument needs to get cold because you want to see the heat of the universe, space is a great place. Here's a picture of the cosmic microwave background, which is on the less than 3 Kelvin. So if you put a basketball in space with a shiny umbrella to shade it, it would, in theory, get down to very close to 3 Kelvin. It would just naturally cool off, just radiate. And finally, why NASA? So our vision for NASA, and the vision is where we want to be, is to explore the secrets of the universe for the benefit of all. I mean, that's really cool. That's one reason why I really love my job. Our mission, this is what we do, is we explore the unknown in air and space, innovate for the benefit of humanity, and inspire the world through discovery. So, for the last 11 years, NASA has been one of the best places to work in the federal government. Any large agency, Department of Defense, Department of Homeland Security, even the EPA, Environmental Protection Agency, NASA has been #1 for the last 11 years. And it's, we got a, looks like a B, 84, which is pretty good. But that's #1. So you imagine some of the other agencies aren't doing so well, right? So why NASA Space Telescopes? To explore the unknown. In this case, I'm going to talk mostly about the application towards astrophysics. Okay, so astrophysics is our scientific endeavor to understand the universe and our place in it. And these are the guiding questions that the NASA astrophysics community uses. So how did our universe begin and evolve? How did galaxies, stars, planets come to be? And finally, are we alone? Okay, that's a big one. That's really gaining a lot of momentum. Okay, so quick talk about money. Whenever you're working on a project as a grad student or undergrad, it's always good to have an idea where that money comes from, because sooner or later it may run out. So in units of billions of dollars, the U.S. taxpayer gives, and there's about $5,800 billion that the U.S. government spends. And of that, 26 per year goes to NASA. And of the 26, about 7.6 or so goes for science missions. It's a science mission directorate, we call it. And in the science mission directorate, the money gets divvied out to earth science, planetary science, heliophysics, or studying the sun and the sun. But then 1.6 goes to astrophysics, and that includes all the space telescopes that I'll talk about. So that's about $5 a year per U.S. person. Being spent on astrophysics. So, a latte, if you want to think of it as. So we get all this money per year. How do we decide what to spend it on? Congress doesn't necessarily just give us the money and say, hey, NASA, build a bunch of cool telescopes. So what NASA does is we basically ask the world scientific community. So we engage them and say, hey, what should we build? And we do this through the National Research Council, which is part of the National Academies. And the National Academies is a group based out of Washington, D.C., that was established in 1863. So it's been around a long time, and it actually was signed by President Lincoln. They provide independent, objective advice, and a lot of people, so what they do is they gather a bunch of world experts on astrophysics, and they put them in a committee for a year or two, and they say, tell us what the priority should be for the next decade. Okay, so once a decade, this is typically done. And this is what they publish. They publish these books called decadal surveys in astrophysics. And so it started in '72, and there's been one every 10 years or so, 82, 91, 2001, 2010, and there was just a recent one done in 2021. But basically, that's kind of the rest of my talk. Here's our table of contents, but I'm going to spend a lot of time on the James Webb Space Telescope. But first, okay, we're at a university here. I'm an optical engineer. And I didn't look at the optics curriculum at Purdue, but I imagine there could be some improvements. So I'm going to give you a quick crash course in optical design of telescopes. Okay? And it's based upon Dietrich Korsch's book, Reflective Optics. He was a NASA engineer as well, published in 1991. It's a great book, but if you're not a designer, probably not worth getting it. But most telescopes are reflective, and the reason why is because big mirrors are easy to make. Big lenses are harder to make, and they're very heavy. And that's one of the main things. So here's the one equation that I hope you'll take away if you don't know it already. There's a few others I'll show that you don't have to take away, but know that they exist. And that's the basic idea of what an F number and an entrance pupil is, because I'll be telling you what these are for each one of these telescopes. Okay, so the entrance pupil diameter is basically how big is your aperture stop? What's the collection area? And since on a telescope, it's typically your first mirror in the system, the big primary mirror, that's just essentially the diameter of that. And finally, if you think of the telescope as light coming from far away, collimated light, and then that focuses down, the distance for that to focus down, if you assume it's just one mirror, is called the focal length. And if you take the ratio of the two, the focal length by the entrance pupil diameter, you get something called the F number. And so the F number is just a number, and this is on your cameras. F-stop is another word. The smaller the F number, the faster the system is, the quicker shutter speed you can have for your camera. Okay? So focal length, entrance pupil diameter, and F number. And here's a plot to give you an idea, and this should be obvious for most designers out there or engineers out there. But on this plot are 3 different types of telescopes. A 1-mirror telescope, 2 configurations of a 2-mirror telescope, so that means a primary and a secondary mirror, and then a 3-mirror telescope. So on the x-axis is the field of view, so that's how big of a field we can see. Okay? On the y-axis is the wavefront error, and that's just a metric for how good the image quality is. Ideally, you want it to be 0, right? But often, over a large field of view, you can't correct that. In fact, that's the fundamental problem for optical design. How do you have the best image quality over a large field of view? And speed, f number. So for a one-mirror system, you get this sort of linear plot. And that's essentially just an off-axis parabola, or some sort of parabola. If you imagine a hot dog cooker you made as a kid, right? Ideally, you want it to be a parabola because you want all that light to focus directly on where you want the heat to concentrate to. But the performance is linear in nature, and it gets worse in your field of view. It's theoretically perfect at the center of the field, but it gets bad really fast. Now, with 2 mirrors, you can turn that into a quadratic nature, right? So more degrees of freedom, the better image quality you get. And 2 mirrors is essentially what we use for the Hubble Space Telescope. Now, for 3 mirrors, you can really, really drive it down because this reduces a lot of the blur in the system, this wavefront error, and it allows you to get a really big field of view. And that's essentially what we used for the James Webb Space Telescope. And in fact, most 21st century telescopes are approaching this 3-mirror concept as opposed to the traditional 2 mirrors. So here's an example of a 1-mirror telescope. These are still used when you have a very short wavelength, because when you have either nanometer, or excuse me, ultraviolet or X-ray type systems, you want to have as few reflections as possible, because every time you're reflecting, you're losing energy. You're losing that signal that you want to see from far away. So you'll sacrifice a large field of view just to give yourself, this higher signal to noise on your detector. And this is a traditional Newtonian telescope, and a recent mission was NASA's FUSE mission, which is a far ultraviolet spectroscopic explorer. The equation for a 1-mirror telescope is quite simple. The curvature of that mirror right there is simply 1 over twice the focal length that you want. How easy is that? Okay, optical design for 1 mirrors is pretty simple. Okay, and in mirror systems, typically you want to use conics, because conics are stigmatic. They provide the ability to take a perfect point and focus that at another point elsewhere. So for 2-mirror telescopes, this was a popular form for the 20th century, and that's a traditional 20th century design. They're referred to as a Ritchie-Chrétien telescope. So 2 mirrors can correct 2 aberrations. Now, an aberration is a term that refers to how bad a system is, and there are third-order aberrations. The classic third-order aberrations start with spherical, and with 2 mirrors you can correct spherical, and the second worst one, which is coma. That was that linear term that we saw in the previous plot. With 1 mirror, you just get spherical. You always want to get spherical aberration corrected. But our field is limited by astigmatism. So that's the astigmatism is the same thing you might hear when you go to an eye doctor and say, oh, you have astigmatism. It's just the change in focus between the x and y axes. Here are the equations to solve for a 2-mirror telescope. So they're starting to get a little bit more complicated. We have 2 curvature equations that are simply functions of the distance between the mirrors and the focal length. And we have solutions for the actual conic constants, which are no longer that -1 being the parabola solution. Okay? So moving on to 3 mirrors. So this is Dietrich Korsch's big contribution, is that he solved the 3-mirror telescope equation back in the 70s or 80s. And so as a result, we started seriously thinking about these 3-mirror solutions for telescopes. And lo and behold, James Webb is a 3-mirror solution. Now in this picture, you'll actually see a 4th mirror, but that's just a flat right there. So it's just folding the beam backwards. So with 3 mirrors, you can correct all your blur terms, spherical, coma, and astigmatism. You've got high-order stuff, and a little bit of curvature in the back end, but that can be resolved by the instruments. And here are the 3-mirror equations. So they're starting to get a little bit more complicated, right? And a bunch of functionality between the mirrors. But anyway, it's solved for. So as an engineer, our mathematicians have laid the foundation for us, right? So, oh, great, I can take those equations and now I can actually build something, which is kind of nice. Okay, and finally, 4-mirror telescopes are starting to appear on the horizon. They look a lot like the 3 mirrors, except that that 4th mirror now has a little bit of curvature in it, and it does some correction for distortion. And distortion is important. Even though it doesn't cause blur, it changes what your object looks like to, it squeezes it or pinches it or pulls it. But if you have a scanning system, that's important. You don't want to have any distortion in your system. Again, all of the aberrations are controlled, and it looks a lot like that. So if you're into design, the next big field that's coming up are what's called freeform mirrors. So instead of constraining the shape of your optics to be a convex, like a parabola or an ellipse or a hyperbola, we're starting to bend them like potato chips. And by creating that sort of potato chip bend, you can really increase your field of view by quite a bit. In fact, this is a favorite plot for optical designers. It's called a bubble chart, where on one axis we have the numerical aperture, which is the same as the f number. It's just the inverse of the f number, so the f25 all the way to f.5. And in the other axis, we have field of view. So with a smaller f number and a bigger field of view, things get tougher, tougher, tougher. In order to get, if you want that telescope with a 50-degree field of view at f1, currently there's no design concepts that can achieve that. These are all typical telescope-style designs, 3-mirror anastigmat, Schmidt-Cassegrain, but freeforms allow us to explore that space. So that's kind of the future of optical design. But it comes at a cost. You break your symmetry in your system, so that means they're harder to align, they're more sensitive. Sometimes they can be less sensitive to perturbations in the system, like if you have a thermal gradient or something. But anyway, so that's the future. Freeform is the future for design. All right, so back to our decadal surveys. Okay, Hubble Space Telescope. So that's a 2.4 meter entrance pupil diameter. Okay, so it's I can probably jump up to it, but it's a nice big primary mirror. It's got a reasonable field of view, and it's an f24 system. Okay, this is what it looked like. There's a big story. It launched in 1990. And there was a problem with the primary mirror you may or may not have heard of. Largely it's being forgot of in today's youth, but back in has published H papers, each of which have been cited in other places at least H times. So it's sort of an area type thing. But number one is Hubble, 257, right? So with 257 papers published by Hubble were cited at least 257 times, right? And then if you look at all these observatories, there's a few ground-based ones next, like the Keck, VLT, but then comes the next space observatory, Spitzer, right? And then the ground-based VLA, Chandra is a space-based, XMM Newton space-based, ground, Fermi space, and then down at the end we've got Sophia here. So this is an airborne observatory, and I'll talk about that in a little bit. But it's pretty low compared to the well-performing other space-based observatories. Hubble is for everyone. If you want to ask Hubble to go take a picture of something, you can do that. You just have to compete against a bunch of professional astronomers and that sort of thing. But every year or two, there's a new round of proposals that you can do. Okay, moving on to 1982 and 1991, Chandra and Spitzer. So Chandra is an X-ray telescope, and it's about half the size of Hubble, an entrance pupil, but we're dealing with X-rays now. So it's actually a whole bunch of nested shells of mirrors, because when you want to reflect X-rays, you have to be at a grazing incidence. So that you just want to basically give it a very, very small reflection. It's a Walter Type 1, which is essentially a 2-mirror Ritchie-Creation style design, but it's just oriented slightly differently. And it was launched in 1999. By the numbers, Chandra is doing fantastic. It's still producing science. And shortly afterwards, in 2003, we launched a Spitzer infrared telescope. Now, this was only a 0.85 meter entrance pupil, okay? But it had a really big field of view. And this one, so that James Webb is coming up, and it looks very different than James Webb in that this is all constrained. Basically, it's a constrained telescope. It looks a lot like Hubble. It's a 2-mirror design, a Ritchie-Creation design. But in the back, there was a cryostat, essentially a big block of ice to keep everything cold, because you want things to be cold when you're looking in the infrared. So James Webb is slightly different. It's wide open because we wanted to radiate its heat away. But anyway, Spitzer was highly successful. Here's some completed its mission in 2020, so we're not using it anymore. It's in a drift-away orbit away from the Earth. Here's some of the main science that I liked. But the TRAPPIST system, these are actually being studied by James Webb right now, looking into the TRAPPIST system. And these are planets that Spitzer discovered around the TRAPPIST system. All right, so Sophia was an airborne-based observatory, about the same size as Spitzer, but on the side of a 747. And the idea is that you can still get above a big part of the atmosphere and be able to, get good science. But the scientific productivity, in fact, that metric that I pointed out, how Sophia was very low, it was just determined that it's very expensive, it's not producing the science, so why don't we use the budget for other things? So this is being decommissioned. All right, so next, James Webb Space Telescope. This is what I've worked on for 20 years. I became a postdoc, and the next generation Space Telescope, which is what it was called back then, actually hired me to do design work for the James Webb. So I've worked on it a very long time. So the entrance pupil is up to 6.5 meters, okay? So compared to Spitzer, which is less than a meter, so that means there's a lot more collection area right here. And if you notice, the primary mirror is not just a single mirror, but there's 18 segments, okay? And each one of these segments is about 1.3 meters flat to flat. And there's 4 main instruments in the back: near-infrared camera, mid-infrared camera, fine guidance sensor, and a near-infrared spectrometer. So the science for James Webb is essentially to look into the past, because since the universe is expanding, any sort of stars that you see far away have Doppler shifted into the infrared. So by building an infrared observatory, you can see further back into the past. And so from left to right, or the Big Bang's on the far right here, here's modern day. Hubble can only see so far back into the, and you classify how far back you can see by what wavelength you can see into. So Hubble can see all the way essentially into the near infrared here, but James Webb can really see where the first galaxies are forming into the early universe after the Big Bang. So I like to say we're taking the baby pictures of the universe. So how do you get cold? In order to see in the infrared, you have to be cold. So you want to get it far away from the Earth, because a lot of that light reflecting from the Earth and Moon generates heat. And you want to hide in the shade. So that's what James Webb does. There's this huge sunshade here. It's the size of a tennis court that puts the telescope portion completely in the shadow. So it's just radiating its heat out to the 3-degree Kelvin universe that I talked about. And the place that we put it is about 1 million miles away, 4 times the distance from the Earth to the Moon. So Hubble, on the other hand, is actually orbiting around the Earth. And every 90 minutes or so, it goes in and out of the shade. So Hubble, has to do a lot of dancing on how it does observations. And sometimes it orbits multiple times in order to look at the same spot. And then it just keeps co-adding all of the data. Well, James Webb is in a nice location in that you can just stare at it the whole time and not worry about changes if you have a nice stable observatory. The temperatures range by quite a bit. So if you, in terms of Kelvin, 0 degrees Kelvin is absolute zero, which is about negative 459 degrees Fahrenheit. The spacecraft is essentially at room temperature. That's where all the electronics are that talk with the ground. That's where the reaction wheels are to steer the observatory. But the observatory itself, the telescope, is in the 30 Kelvin range, 30 to 50 Kelvin. The coldest one being at the secondary mirror, because that's just hanging out there. And away from other hot spots. The instruments are very cold. We do have one cryocooler for the mid-infrared instrument, which gets us down to 6 Kelvin. Okay, so that's looking at wavelengths up to about 28 microns. And there isn't a hot instrument pack because the cabling would have been too long to put it down here. The instrument electronics are pretty hot compared to the spacecraft, but we have these radiators to get rid of all that heat as much as possible to prevent any impact on this. Now the sun layer itself, if you notice, there's 5 layers, right? If you're trying to stay warm, right, you always want to put layers on to keep yourself warm. Well, the same thing if you're cold. So 5 different layers on the sunshade, and this is a Kapton material, sort of that space blanket, but a little bit tougher. And the temperature just drops down in each one, and it's flared, so the heat just radiates outward, and it's really tight on the inside and flared on the outside. Here's the optical design for James Webb. So this is the stuff that I worked on. And again, it's 3 mirrors. We have a curved primary mirror, curved secondary mirror, curved tertiary mirror. Now this FSM is a fine steering mirror. It's just a little tip-tilt mirror to keep us pointed at where we want to be pointing, but it's a flat, so it really doesn't count for aberration control. But it is located at the exit pupil. So that means that if you take the primary mirror and you re-image it by the first 3 optics, or the first 2 optics, it actually lands on the fine steering mirror, so you can do a good job of steering where the image is. It's corrected for those aberrations, as I mentioned. Here's what the mirrors look like. This is what a single segment looks like. And they're all coated with gold. Turns out gold is the best reflector for infrared type imaging. It's just over 99% or something like that reflectivity. So that's what you want. For light that we see, silver is, or more of a silver is type of the reflector that you want. So let's flash back a little bit. This is where I work at NASA Goddard Space Flight Center, and we have the very, very large clean room there, and that's where the telescope was actually built. If you look right here, you'll see a shiny bald head. That's me. But this gantry system right here is where it was built. It was put upright, and you could actually take a selfie in there, and that's what our Nobel laureate, John Mather, did. We call this a $1 billion selfie because it's a very expensive telescope, and these are all our communications folks right here. But yeah, right before we shipped off James Webb, we turned it towards the viewing display, and everybody got to sort of take one last goodbye for it. It went through a lot of testing down in Houston, and then it finally arrived in Los Angeles at Northrop Grumman in order to be assembled to the spacecraft. So here is the folded up sunshade. And these are the part of the sunshade system. But here's the observatory, and it was integrated to that. But if you look closely here, so I'm an optics guy, optical engineer. What's the most embarrassing thing that you can do when you're trying to take a photo of somebody, right? Say, I can't see anything. If you have one of the old school cameras. Oh, I left my lens cap on. Oh, silly me. Well, if you look at that closely right there, remove before flight. Okay, that is the lens cap for James Webb. And I had an extreme interest in so as a designer, I don't touch the hardware much. I talk to the people who touch the hardware. They're technicians, they're experts. So I had an extreme interest in the person who was doing this, removing this lens cap. Say, did you get it off? Is everything okay? Anyway, so yeah, he said, yep, we got it. Larkin Carey at Ball Aerospace, he did that. And so there, that's what the lens cap when it's taken off of James Webb looks like. Essentially, this is think of where all the detectors are. You can imagine square detector here, a bunch of square detectors here, and an angled square detector here. It's just an internal image of the focal surfaces of where they'll be. And that's what it looks like. So this moment was big, and one of our engineers duplicated it in the world of Legos because they thought it was a big moment, because you want to leave that on as long as possible, because that becomes a source of dust to come in and land on your optics or your detectors, and you never want that to happen. So you always remove it at the last minute. So Christmas morning, 2 years ago, was a really big morning, and here we go. And that's when James Webb launched. So once everything was ready to go, it was really, it was one of the few times that I've waken up before my kids for Christmas. This was a big day. All of us were dialed in. We had these big network parties between all the houses, and it was a really cool moment for all the JWST engineers.
Begins a voyage back to the birth of the universe.
Okay, so that was really big. This is the goodbye picture from the spacecraft that was basically sending James Webb on, and this is one of my favorite shots. This is, it doesn't look like the telescope or anything. This is kind of the butt end of JWST. You know, there's propulsion here. This is all spacecraft here. So all of the optics and everything are on the other side. And so deployments, right after deployment, the first thing that happens, you know, this telescope is so big that it has to be folded up into the fairing of the rocket. And so there had to be a huge number of deployments, 50 major deployments, all successful. Okay, so this is our mechanical engineering team just practicing again and again and again to make sure it's right. And each one of these mechanisms have to be tested in a flight-like environment where you're shaking it, you're blasting it with noise, and such that it works. And all of them worked. I mean, it was really, really exciting. And this is what made me the most nervous, actually, was this sunshade when it deployed. Because I got to look up close to it once in one of our later testing. But if you're a sailor, you know, if you have an appreciation for all the lines and pulleys and cleats, and I mean, there are a lot of moving parts to this, and you think, gosh, if one of these cables gets stuck or whatever, and you know, the launch environment is not a a benign environment. Things are shaking and rattling, and so this was a very nervous moment for me, but everything worked out well. You can see the 5 layers coming apart, right? That's critical in order to get the temperature down. Yeah, it worked. Now here's where the optics start to get deployed. So the secondary mirror was on a tripod. It just did that. And the back end, this is our radiator for the electronics that need to get cool. And then we have 2 wings that deploy on the primary mirror. So here's the second wing. And so once this is done, we're not quite done. So all of these mirrors, even though they're in a deployed state, they're not what we call the phase. They're not acting as a single mirror. They're up to 1 millimeter apart. And when you're trying to look at images that are diffraction limited down at 2 microns, that's unacceptable. So then you have to essentially start an extended alignment campaign. But first, let's talk about where it is. So here's a good graphic of Earth and the L2. So James Webb is actually orbiting the L2 point. That's why we have to have some fuel in order to keep us there. This keeps us orbiting around here, and there's a few other telescopes that are here and plan to be here also orbiting this. So this will be a used space. And again, the shade is pointed towards the Earth and Sun, and so such that the telescope can always be pointed, always be in the shade while it's operating. Okay, once we got on orbit and we deployed all the segments, the first thing we did was, okay, let's see if our main camera works, the near-infrared camera, because that's the camera that's going to do our alignment. And lo and behold, we opened up, we point towards a Magellanic Cloud where there's lots of stars, lots of stuff going on, and we're bound to get something in, and this is what we saw. So a bunch of smears and stuff like that. And that's kind of what we expected to see, because the segments themselves are millimeters out of alignment. There's lots of aberration, spherical aberration, coma, astigmatism, those words, and they're scattered all over the place. Okay, so let me review on how we align the telescope. So here's the telescope image again. So there's a total of 133 degrees of freedom. So that's how many knobs that we have to dial in order to make this telescope work like a telescope. So each one of these segments, these hexagons, have a 6 degrees of freedom, so rigid body motion. And there's also a radius of curvature control. So think of it as puckering, just changing the pucker shape of it. The secondary mirror has rigid body control. The tertiary mirror is fixed, so we sort of have to align to that. And then the fine steering mirror just has tip and tilt in order for doing guiding. Now each one of the detectors, or each one of the cameras in the back has its own focus mechanism. So there can be a final focus for that. But fundamentally, the telescope is way out of alignment. And that was the next essentially 3 months of work. So here's the formula for aligning it. First of all, you have to figure out where your segments are in the image, because if you think about it, 18 different segments means, and if they're way out of alignment, that makes 18 different telescopes. So one star will appear 18 different times. Oops, let's go back. Let's see. So we align the segments, we stack them, coarse phasing, which is basically doing a rough job of trying to bring them in the same piston. We do fine phasing, then we align it over the field of view and iterate. So essentially it's a standard optical alignment. You start big, you get the millimeters down to microns, you get the microns down to nanometers. It's just sort of this iterative approach. Okay, so when we first started looking at the sky, instead of looking at that really busy place, we looked at a blank part of the sky where there was one bright star, because that would help us find out where all of the segments were. And then we started scanning. So this is all these images for scan. And if you notice these little green dots, those are the 18 points of the 18 segments that we had to find. And we thought that it was going to be where this red X is, but we accounted for this huge area right here. But it turns out they were all kind of close. So that really excited us. Say, hey, we're close enough. In fact, we were so close, we just stopped the scanning because we found all 18 in this early set. So that was awesome. And this is what it looked like. So the telescope image, by looking at a single star, you get 18 stars. And then you wiggle each segment a little bit, one at a time, and take another image to figure out which segment is which. And that's what we did. And it turns out here's 3 segments on one wing, 3 segments on another wing, and here are all the others right here. So a typical sort of scatter that you might expect. And then we get all these segments, we bring it into a nice hexagonal array such that we can, we know that that is associated with that segment as if you're looking at the primary mirror. And then we do a little bit of focusing on each segment to get it down to a smaller spot. So that's segment alignment. And then we stack it down to a single segment. So this looks like a nice sort of point spread function, but it's really the size of a point spread function of a single segment as opposed to a phased primary mirror. So for coarse phasing, the idea is now all of these segments aren't behaving as one because they have little step functions between them if you look at them from the side. So by changing the pistoning between the segments, we now get them such that they act as a single mirror. And we do that by using a grism, sort of think of it as a prism that causes a lot of this fringing. And we follow the fringe pattern down in order to get that optimal segment pistoning. And then at the end, so the end game is done by a method called phase retrieval. And so what we do is we look at this bright object in and out of focus. So we actually purposely want to defocus it because there's a lot of information in the defocus and these really spread out point spread functions that you can use to determine exactly how you have to change the segments for your final alignment. So this information at the image tells you a lot of information at the pupil when you do a phase retrieval process. And then that information at the pupil tells you how to move the segments. Do we laterally decenter it? Do we change its focus slightly? All that sort of stuff. And that's all in the control, the wavefront sensing and control, we call it, for the telescope. So here's a quick a movie of essentially 2 or 3 months where we took all the images. This is the actual image name in the lower left right here, where it's just, and each image takes about 3 minutes or so to take with a bright object. And then you take a bunch of them, and then we can get data from the telescope several times a day using the Deep Space Network. And then you meet with a bunch of people and say, hey, this is what we see, let's do this next. And everybody says, yeah, that's a good idea. And then you load it back up. So the feedback rate, is on the order of a day or two, right? So this is not, it's not, James Webb is not thinking for itself. We bring the images down. We've got a ground crew that determine what to do, and then we send it back up. Future observatories will be different, but currently that's the alignment method for James Webb. And the reason why these are dancing all over the place is that you get a lot of field knowledge by looking at how the spots change as a function of field of view. So that's only going through the coarse phasing mode. And this was the final sort of fine phasing test image that we did. Again, it's one bright star amongst a field that we thought was pretty blank. But these galaxies, they just kept photobombing us. And that was just a big, surprise. I mean, we knew it was going to happen, but when you see it, it's like, oh my gosh, look at that. I mean, we're just, and this is, we're only exposing the telescope for a little while, and we're seeing all this stuff super far away. And the more red you see this, the further away it is. I mean, it's just pretty amazing. So once you get everything aligned, mostly with NearCam, you check all the other instruments to make sure they're good. In some cases, the instruments can feed back into the alignment. But in our case, it turned out to be good enough, mostly with NearCam. And then we check basically how things look. We look back towards the Magellanic Cloud. If you remember all that noisy stuff, now you're starting to see, wow, I mean, look at all this. This is fantastic. So to compare it to Spitzer, Spitzer's on the left. This was an infrared telescope that had the same wavelength to James Webb, the mid-infrared instrument. So this is flashing back between the capability of James Webb versus Spitzer. So over an order of magnitude. And generally, that's the criteria. Before you want to build something new and send it to space, you need at least an order of magnitude improvement, right? Okay, so here's 3 months all in one slide through that 7-step procedure that I mentioned. We've all seen these. So, quick lesson. When you are looking at pictures from NASA now, if you see something on your favorite news site or whatever, say, new NASA reveals new image of whatever, look closely at it. And you're going to see these, if you see stars in the image, you see all these spikes. These are diffraction patterns, okay? Now, if you see spikes that are essentially like a cross, that is from the Hubble Space Telescope, typically, okay? Because the diffraction comes from these lines here that are holding the secondary mirror for Hubble. Now, if you see something that looks like a 6 hexagonal pattern, it's like 6 spikes, that is a James Webb, and you actually see these little smaller ones that are left and right here, and that's from the upper one. Okay, so whenever you see an image and you've got the 6 pattern, that's going to be the James Webb. If you've got the 4 pattern, that's the Hubble. Image quality, diffraction limited. A star is 77 milliarc seconds, 2.12 micron wavelength. We nailed our requirement. We were thrilled at that. And this was a big one that I was involved with, was stability, right? So stability, if you want to take a really deep image, you have to be very stable. You don't want your telescope to change at all, and you're going to look at days at something. So that's exactly what we did. We pointed the telescope one direction and then sort of created this thermal gradient across the telescope in one way and sat there for a long time. And then we pointed it to the extreme other direction and then looked how the images changed over time. And this was the change, right? So a typical sort of a, thermal type of exponential type change. It started here, big change at first, then it settles out to something else. And that number is less than 25 nanometers, which is fantastic. We were budgeting over 30. Actually up to, I forget what the actual budget amount, but anyway, we have lots of margin here, so it was fantastic. So what do you do when you go through all the tests? Well, if you're an engineer for JWST, we're basically handing the keys over to the astronomers, the scientists. Well, you celebrate. And this is one of my fellow engineers with a $100-year-old bottle of cognac that we all shared. So that was a big moment. You've probably seen some of the science images. I'll talk briefly about this. This is my personal favorite, the Carina Nebula. I just think it's fantastic. Again, you see these 6 points, stars. This one's really neat also because it's a deep image, a deep field image. So you look far away, you stare at it a long time, and there's a lot of cool stuff here. First of all, you can see, there's false color in this. So what does that mean? You take an image with a bunch of different filters, and you apply the filters relatively to what we can see, right? So the filters at short waves are going to be the more blue ones, but the filters at the long waves, even though we personally can't see it, are going to be the red ones. But if you look at some of the really red stuff, that is very, very far away. But you can also see these smears here, okay? And what these smears are is gravitational lensing. So there is a bright object far away, and then there is a nearby object. It could be a galaxy, it could be something smaller in a galaxy, but the light is actually bending around it. And with this gravitational lensing, there's a lot of science that can be done with that. In fact, that's one of the approaches for looking at exoplanets, planets around nearby stars, or any star, actually. So this is kind of a neat image. The spectroscopy is not as exciting to look at, but it's very exciting if you're a scientist because it tells you what you're seeing, right? This is water, water signatures and what's being looked at, but it's atmospheric composition of maybe a planet that goes in front of a star because the spectrum changes. And there's some planet in the solar system. There's been some great images released that. Here's a Jupiter image, and more recently, here's a Uranus image, and here's Uranus with all of the moons. I love it because I'm a Shakespeare fan. So Oberon, Tatiana, Ariel, Puck, Miranda. It reminds you of how the moons are named, and more of a close-up view of Uranus. Okay, so JWST is everyone. You all like Hubble. You can also propose for time on JWST. You're competing against professional astronomers, but this deadline is passed, but there'll be another one. This was back in January. And the final thing I'm going to say is that if you become an engineer on a large project, it's not all about you. You're working with thousands of other people, lots of people. In this case, over 20,000 engineers worked on James Webb. I mean, many, many, many of us worked on that at different phases of it. And 2 decades, just all the different teams and everything. It's just been a fantastic effort. And if you work on a large project, just expect this teamwork aspect that you need to do, especially if it's a national level type project. So I like to say it's like raising a kid, because I spent 20 years on this, from the design all the way to production, and my kids grew up during that time. All right, so moving on, we'll talk really quick about Roman, and then the final one. So the next telescope that we're working on is going to launch in 2027. It's a Nancy Grace Roman Space Telescope, and it actually looks a lot like Hubble. So 2.4 meter primary mirror, just like Hubble. But it is a 3-mirror system. So if you remember, Hubble is a 2-mirror system, has more of a limited field of view, but now we're actually using a 3-mirror system on a Hubble-like telescope for a much bigger field of view, and it has a monstrous detector. It's going to take tons of mirrors and or tons of images. The goal is to launch in 2027. It's named after Nancy Grace Roman, who was NASA's first chief astronomer. She really pushed the focus for doing astrophysics at NASA, and so we felt this was an appropriate person to name the telescope. She's often called the mother of Hubble. Early telescopes at NASA were more for looking at the sun. In fact, there was telescopes on the Apollo program that, actually they were doing looking at the sun for EUV type stuff. But she's the one who said, hey, let's look away from the sun. There's a lot of science out there to be done above the atmosphere. So the main thing Roman is going to study is dark energy. If you haven't seen a plot like this, everything that we can see and sense in the universe is only about 4.6% of it. I mean, it's everything 4.6%. The rest is dark energy, 73%, and there's a big chunk of dark matter. And I'm not an expert on this, but how this telescope will sense this is to essentially survey as much as possible in the universe with this big field of view and look how things are changing as a function of direction. But it also will look at exoplanets. So we have one really interesting instrument on board. It's a coronagraph instrument that is going to essentially look at nearby stars, and it will block out light from the star with hopes that planets next to the star you can see. That's a very difficult problem because it's you need 9 orders of magnitude of contrast. Okay, the star is so bright and the planets are so dim that you have to have a special instrument in order to do that sort of thing. Another approach is to do the microlensing, like I mentioned, in order to do that, and you can have special anyway microlensing. Here's the hardware of what Roman is. It's up in Rochester, New York right now. It's actually a little bit further along than this, but I couldn't find more updated images. Anyway, 2027. Roman will be at Goddard Space Flight Center sometime late next year. So if you find yourself in DC, let me know. And we might be able to give you a quick view of that. The final decadal survey that we just recently had, the recommendation is out. And the recommendation is to make an infrared optical UV telescope that looks sort of like James Webb. I mean, this was just an idea concept that was flown to them. But the scientists don't say build this. They say build something that does this. This is what we need. We need this science. And then NASA will take it on. The engineers, like myself, a big team of us will say, okay, what's the best way to meet these requirements? But here's one concept. And currently it's being called the Habitable Worlds Observatory, HWO, because one of the main missions is to really look at the nearby stars to see planets around them, to see especially planets that are Earth-like, right? They're in the Goldilocks zone. They're so far away from the sun or their star and the size of their star that there can be water and potential life. So that is the main directive for this, and that is just starting up right now. If you want to get involved with the Habitable Worlds Observatory, just released in early April as a Dear Colleague letter, which is a way of saying, hey, we're building this team to consider what needs to be done in order to make the Habitable Worlds Observatory. And this team is essentially anybody, maybe any U.S. citizen, but maybe it's beyond that. I'm not sure. But if you Google just the Habitable Worlds Observatory, you can find this from the Astro 2020 portion of NASA. And the name of the team is the Science Technology Architecture Review Team, START. And the idea is just to lay the foundations on what a yardstick, on what this what it will look like. What is this going to look like? Okay, since I'm speaking to a bunch of students here, I often get the question of, hey, I want to work at NASA. How do I get involved? So the main thing, we have lots of internships. So at Goddard, there were almost 300 interns every summer that we get. And the website is just intern.nasa.gov. It's very simple. So that's the main thing to do, is what I recommend. But if you want to, if NASA is your dream to work for there's something called the Pathways Intern. Okay, so a Pathways Intern is like one level above. It's like being a co-op for NASA, and once or twice a year a call comes out for that, and you apply. And if you get hired as a Pathway Intern, you become a NASA employee, but you finish your student career either as an undergraduate or a graduate student. And during that time that you're finishing, you work at NASA at the summers with full-time pay, benefits, and all that sort of stuff. And then when you go back to school, you're back at school. We don't bother you unless you want to. Actually, a lot of the students continue to work because they love what they do. And that is a fantastic way in. In fact, most of our new employees come through this Pathways internship program just because it was brought out 10 years ago, and that's just that's what we need to do. And so we basically get you early and then bring you in. There's many fellowships out there, so if you're a graduate student, there are technology fellowships for specific technologies that you can apply to for NASA. And then there's a great postdoc program as well. I'm one of the postdoc mentors for space optics, optical design mainly. Anyway, lots of ways to work at NASA. Finally, that's it. Thank you. So, any questions? Also, if you didn't get any, I brought a bunch of stickers, NASA, James Webb, Roman Space Telescope. They're in the back, a little table on the left-hand side, so grab something on your way out. And bookmarks as well. Yeah.
So I'm going to start with a question. Is this mic on? Can we get this one on? Okay, good. So you said that there's this kind of slow iteration loop for the alignment. But you said future telescopes might be different. Do you have more to say about that?
The question is, there's this iteration. For James Webb, we had this slow iteration loop to align it. And so the philosophy on James Webb is that we would align it, and it would stay in that alignment as good as possible. And our performance requirements were such that the drift associated with James Webb would be most of the image that we would take would be good enough. Well, for habitable worlds, in order to see these exoplanets, for the coronagraphy to work well, things need to be extremely stable, picometer level stability, okay? So if you mechanical engineers out there, that's like super, super small, smaller than an atom, okay? Picometer level stability will likely require some sort of feedback loop that is on board, such as a laser metrology system. So imagine lasers pointing at individual segments to make sure that the individual segments stay within that piston level, that they're acting as a single mirror, and that there's a feedback loop on board in order to maintain that shape, as opposed to sending images down to Earth, processing it, and sending it back up. So that's one concept, like an onboard laser metrology system. One can imagine a onboard, phase retrieval type feedback, or even just a pupil-based Shack-Hartman type system or something like that. But anyway, that START committee that I mentioned for habitable worlds is going to investigate all the sort of needs for that and prioritize the technologies that need to be improved before we start building it. And then once you start building it, you kind of want to freeze your ideas of what technology you're using. Otherwise, you're always trying to hit a moving target as you build something.
Questions?
So you said that the telescope moved across the United States. How do you move it without it being damaged in transportation?
Yeah, so that's a good question. I don't have the picture in this slide package, but we actually have this large container. So the telescope, before it's moved from, let's say, Goddard, where I work, to Houston or even to Los Angeles, we actually folded up the telescope into its, like it goes into the rocket fairing. But then we have this, looks like a Quonset hut. It's flat on the bottom, curvy on the top, and very long. And it's designed such that it slides in the back of a very large C5, I think it's an Air Force C5 Galaxy. So if you're familiar with Air Force planes, it's a big, huge cargo plane. One designed for doing payloads, for carrying payloads for rockets, for mostly military, but NASA borrowed it for a couple trips. But once it got to LA, this container had to be switched to a different container because we put the spacecraft on, right? I think it was a different container, but anyway, it looks similar. But from that point, we couldn't fly it anymore, or the launch facility didn't want us to fly it because the location of the launch was actually in South America, because the Europeans, part of their contribution was the rocket itself. And for all of their payloads, they always bring things into port. So literally, it went on a barge from Los Angeles through the Panama Canal all the way down to French Guiana, which is their launch facility. So yeah, it's basically a big Quonset hut that we build around it. It's positive pressure to keep any moisture or air coming in, so you're always bleeding nitrogen through it and all that sort of stuff. And it's wrapped up and clean as you can get it. Good question.
Really enjoyed your talk. Thank you. Sorry.
Hey.
So, couple questions. As you come in with an optics background, how much of the non-optic stuff on the telescope do you work on? And then also in the past 20 years that you've been working on this, do you get to work on other projects, or are you mainly focused on iterating on the telescope? Just interested on what that looks like.
Sure. So the beginning was, so the question is, do I work with a lot of other engineers besides optics, I guess is a way to phrase it, or non-optics type stuff? So one of the cool things about being an optical designer is at the beginning of a project, and I was hired as a postdoc early on, right, is that you get to interact directly with the customer, right? And that customer are the astrophysicists, the astronomers, the science community. And they are very intelligent people. They know a lot about exactly what they want, and they actually know quite a bit of optics as well. But some of the details in getting the design, just that interaction of speaking with that community is just wonderful, because you learn about what they're doing and they learn more about what you're doing. And a lot of those professionals actually work with us the entire cycle of the 20 years of what we work on. Because sometimes we get to a point where, oh, we got this problem with this one detector. Is that okay? And it always goes back up to science and say, well, it's going to be the problem with this one little requirement. Do we modify the requirement, or do we use the backup detector and reinstall the backup detector? So there's always those conversations going on. And whenever you change things, schedule is impacted, cost is impacted, things keep moving to the right, as we say. So yeah, as an optics person, I deal a lot with the scientists and mechanical engineers as well, because hence, if you're into optics and you're a mechanical engineer, the world doesn't have enough optomechanical engineers. So go and get a graduate degree in optics if you can, and you will have no problem finding a job, in my opinion. Maybe that's changed, but optomechanical engineering is mechanical engineering basically, but now you're dealing with tiny little tolerances as opposed to an inch. That's good enough to build this bridge or whatever. No, we're dealing with nanometer level tolerances. And the second part of the question was, over 20 years. Yes, so James Webb was the majority of my time. However, Roman used to be called the Joint Dark Energy Mission 5 years ago, and we were doing early studies for that. This Habitable Worlds Observatory, there were 4 different studies submitted to the decadal committee, 4 different concepts. 2 of the 4 concepts I worked on. So that's about a quarter of my time doing that, because even though I call myself an optical designer at NASA, I do optical design less than 20% of the time. It's mostly analysis and engineering type activities. So yeah, there's plenty of opportunity to do as much as you want. In fact, NASA engineers often take the work home with them, and it's just becomes a work-life balance issue, just because it's a lot of fun, right? And many of you have that issue as well, I'm sure, especially if you're a grad student trying to finish up.
So quick question about the Habitable Worlds Observatory. I know that you said you try to look at nearby exoplanets. So I was curious if you guys have like a maximum distance right now that you think you'll be able to observe, or like where you think I know it's still pretty early stage, but like where you think you'll at what distance are you trying to look up to like observe these exoplanets?
Yeah, good question. So I'll try to answer this the best that I can, not being an astronomer. So it's not just about distance. It's also about how far away the planet is from the star, right? So you can imagine a big lukewarm star as opposed to a small super hot star, right? The Goldilocks zone will be different for each. And so if you're further away from the star, it's that angular distance that's kind of important. So, but it's easy to think of as distance. And the metric that's being used and the circles on how good a particular design is of the known stars that we see nearby. We can sense that there's something there by watching the star jiggle, right? When a planet's orbiting a star, you can actually see a little bit of motion forward and back. You can see the kind of a Doppler effect. Sometimes you actually see the star dim a little bit because the planet goes in front of it. And so of the certain ones that we pretty sure that there are planets around, and Kepler did a good job for finding a bunch of planets. We put them through a design formula to say, okay, with this particular telescope design of this set, we can see up to 30 Earth-like objects within the 5 years or something like that, because you have to spend a lot of time adjusting and doing that sort of thing. So that metric on how many you can see is important, and generally they are close by, but I don't know the specifics of that. Sorry.
Thank you for the awesome talk. I had a question on how was the manufacturing performed? Was it in plant, or is there any considerations on outsourcing them? And what's your idea on implementing additive manufacturing for these, like manufacturing the telescopes?
So I heard additive manufacturing in the second part, but was that also the first part?
The first part is just about manufacturing.
Oh, manufacturing. The general way NASA builds things is that we'll contract to industry for most large items, especially when industry can do it. But if industry can't do it, then we'll try to do it in-house. So for example, for the James Webb Space Telescope, the telescope aspect of it, there was a prime contractor, Northrop Grumman, who was in charge of building the telescope. And they also did the spacecraft as well. But the optics on the telescope were done by a subcontractor of theirs, Ball Aerospace, did a lot of the polishing, and they were also in charge of the alignment of the observatory and that sort of thing. So the manufacturing gets trickled down to many subcontractors, and NASA's role is we need to be a smart customer. So we have a large engineering base, including myself, optical engineering, and oftentimes we'll visit these sites and, and develop their requirements, say, okay, we need a telescope that has a 6.5 meter diameter. And oh, by the way, here's a design that we think works, but you guys figure it out. And their design comes back and says, oh yeah, it looks a lot like this, and that sort of thing. So that is typically how it works. Now, for the additive manufacturing aspect, we've been looking at that quite a bit in our own internal research and development, but also it's pretty exciting, actually. I mean, from a mechanical engineering perspective, right? So as an optics guy, I design, let's say I design 2 or 3 mirror system that goes to a detector, right? That's all I'm doing is 2 or 3 surfaces, right? Held, just give me 1 micron of surface of reflective material, and I'm good. Now, you mechanical engineers figure it out. And then, so with additive manufacturing, especially with the, I forget what it's called, but where they can make the supports for it, but they can also use a sort of dynamic, this spider-like structure that forms itself to find the least amount of material, the stiffest to hold it, that sort of stuff. There's a word for that, I forget, but it's a new sort of design. I'm sure that there's some going on here at Purdue, actually. But that's pretty exciting, and we're looking at, you always start with small stuff, small missions, that sort of stuff, because it's any new technology, from an engineer's perspective, you test it out many times first before you put it on the big expensive stuff. And we have looked at additive manufacturing just for mirrors themselves, but you have to be careful about the surface and stuff like that. Anyway. Yep.
Hi, thank you. I guess 3 questions. What optical software do you use for design? How does light get from the main mirrors to the 3 individual detectors? And then finally, in the case of the slitless spectrometer, do you ever have to deal with overlapping spectra? And how do you end up distinguishing between them if that's the case?
Okay, so the first one, what engineering software do I use? So I actually use the 3 major ones. There's Code 5 from Synopsys. There's Emacs from, I think ANSYS purchased Emacs recently. And then I'm one of the old school guys who, when I was doing my PhD, I used Oslo, which is Lambda Research. But for James Webb, the majority of analysis work was with Code 5, because there's a lot of industry partners were using that. We just decided that let's just settle on this. But any of them sort of work. They all do the proper physics. And it's mostly geometrical optics that you need for that. The second question was, I'm starting to forget now.
Getting the light to the 3 detectors.
Oh, okay. So for the different instruments of James Webb, is that okay? So how does the light get there? Well, it goes through the telescope, so that's 4 reflections, and then when it gets to the instrument itself, the instruments have their own relay optics. So, for example, for the NIRCam instrument, there was a collimation lens assembly that was 3 different lenses to take the light. So the telescope focuses down to a point. So now you're looking at something like right in front of you, like look at the seat in front of you. And now from that point, you have to relay it to the detector. And for the near-infrared camera, for example, there were 3 lenses to collimate that light from where the telescope image was coming to. And once the light's collimated, it forms a nice pupil, essentially, which is an image of the primary mirror. And that's where you want to put all your filters. Typically, any filter or any sort of like a spectrum, like a slitless spectra that you mentioned, like a grism, you want to put it a pupil because it'll be the same for the entire field of view when you do that. So that's the natural location for that. And then once light goes through the filter or whatever, then you have a follow-on camera, we call it, and it's 3 lenses to focus it down to the detector. Now that's the near cam. Other instruments are reflective, just like the telescope, so you'll go through typically 2 or 3 reflections in order to do the same thing. Mirrors are nice in that you don't have to worry about as a reflective optics guy, one disadvantage of lenses, I like to say, is that the refractive index changes as a function of wavelength, so you have to account for that. You get your color aberrations. However, they can be quite small, which is nice for lenses. Mirrors are they have their own advantages. So. And does that answer your third one, sort of? Oh, it's, the separating of the spectra. So yes, you're kind of stuck with overlapping spectra sometimes, but in fields, what astronomers do is they know what they're going to look at because we have databases of the sky that we're going to look at. At a certain time of year, things rotate from each other, and you know the alignment of how your dispersion is, and so you try to schedule a photo or an image for a certain time of year that you get the least number. But on the James Webb, we do have one special instrument, the near-infrared spectrometer, that actually has an internal image. So that's think of it as being where the detector is, but there's optics between that and the actual detector. It's a micro slits. So imagine basically a whole bunch of shutters that you can address and open each one of these shutters to prevent that from actually happening. And it was a micro shutter array, MSA, that we built for that. About 100 micron size micro shutters, 100 by 200 or 200 by 300, something like that.
I have a question regarding the testing that is done for the telescopes. So I was wondering, when you build such large telescopes before launching them into space, what kind of optical testing goes to ensure or to give you confidence that it will work the way you think it should? Because you can do mechanical testing of parts and components here on Earth building prototypes, but when you build such a large telescope, there's nothing that you can do on Earth to ensure that it will work. So I'm just wondering about that.
Yeah, so that's a great question. We call that verification. How do you verify that your telescope is working or your instrument? And what we do is as we build it up, we try to give it the most flight-like test that we possibly can at each stage of integration. So let's start with the mirror. You take one of those primary mirror segments. We polish it to the exact shape that it should be, coat it, and then you can test that optically directly, just by itself, using a null system, just to see if the wavefront coming back from the mirror is what we think it should be. Great. Okay, now let's put that mirror in the structure. Now, if the structure is not too big, if it's like in an instrument or something like that, you can take that full structure, test it in a flight-like condition, meaning you put it in a vibration chamber, you shake it like it launches, you put it in an acoustic chamber, you blast it with all the noise from the rocket, and then you test it again. So that's called exposing it to a flight-like environment, retesting it to make sure it hasn't changed. Now, at some point, the system is so big that you cannot optically test it, is what you're sort of pointing out. And so we try to make sure that each sub-system level test is completed, and then we try to test it as much as we can at the level of the biggest level of integration. And so for James Webb, what we did was down in Houston, Texas, we assembled the system, and when you build things for space, you want them to be light, because every pound, every kilogram that you send into space costs a lot, and you're limited by the rocket that you launch on. And so our primary mirror segments actually bend a little bit under gravity, but we know how much they bend because we can test it. But while at Houston, we actually looked at the primary mirror, the full primary mirror together, and phased it up using an interferometer, and we knew what the target would be on what it should look like on Earth as opposed to space. And so you can sort of modify the testing and say, okay, under gravity, it should look like this. And we know that our models for gravity are really good, and so we can project what that is going to space. So I guess the basic answer is we depend a lot on modeling, and very good modeling, and we have to validate and verify our models the best that we can to the hardware that we're using. And it's going to be a more challenging problem for the Habitable Worlds Observatory because that's going to be even bigger, and it's going to require extreme stability. So yeah, model-based verification is becoming really big.
Throughout your presentation, you talked a lot about how the mirrors have improved for the telescopes, but I was wondering how much the detectors themselves in the Space Webb telescope have improved and how significant that is for the telescope as a whole.
Oh, for James Webb, one of the technology developments that we spent a lot of time and resources on was those detectors, right? Because the infrared detectors existed in some form, mostly for other agencies' applications, but we wanted specific ones for this wavelength band in order to work that were for the full wavelength band, for the level of sensitivity that we wanted. And so we actually went through a couple rounds of purchasing new ones to make sure that they were okay, because some of the original ones were starting to degrade over time quicker than we expected. So yeah, detector development is key, and even in other projects that I work on for design efforts, it's in fact in the earth science field, the phrase is it's the detector dummy. It's always about the detector. I mean, so the detector is very, very important for all of this. In the traditional optical design field, I'm working in a field that people have been doing for centuries, right? How much more do you need, right? I've been studying for hundreds of years. Well, freeform is kind of a new thing, right? So it's a slowly evolving field, but the detectors are not. I mean, that's really where a lot of new work is done. So.
Well, thanks so much, Joe, and anybody who has additional questions can come and ask him afterwards. But well, thank you once more time.
Hey, thank you. We got a Roman shirt here.
That was terrific. I actually have a bunch of questions.